Alright guys, I just want to talk about finishing up the 7.1 PowerPoint. Just to go through some examples here, just a couple properties towards the end that are very important. Just talking about some ratios and how we use ratios. It says a designated hitter made 8 hits in 10 games. Find the ratio of hits to games. 8 hits to 10 games. Okay, that reduces to 4 to 5. Okay, hits per games. Okay, so what it basically is saying is I need to play 5 games to where I can get, so I can have 4 hits. This is a situation where even though it is a ratio, I cannot change hits and games to the same unit. It's not a big deal. What we would say is we basically, if I were to put this into a decimal, it's 0.8 hits per 1 game. Okay, so I'm getting a little bit less than 1 hit per game if I look at it that way. Here it says there are 76 boys in a sophomore class of 165 students. Find the ratio of boys to girls. This is a common problem that like end of course exams will write, because they know that people are, they go see 76 and they see 175, and people are going to go 76 to 165 and be done with it. Okay, but that is boys to students. And if you look at what they want boys to girls. Okay, well, if I've got 76 boys, 165 students, okay, so I'm going to have 76 boys on top, and on the bottom should be 165 students minus the 76 boys. If I do that difference, won't that tell me the number of girls that I have? So if we do that, 175 minus 7, or 165 165 minus 76, so 89. So 76 boys to 89 girls. Okay. The 76. Do these numbers reduce any? I don't think so. This next one is kind of what we did with the extended ratio, but it's not an extended ratio. Basically, we said we've got this cable. It's 42 feet long. Okay, it's a total of 42 feet long. And we have it divided into 2 parts. So part 1 and part 2. Now those 2 parts need to add to give me 42, but when they reduce, they're in a 3 to 4 ratio. So one might be 3 and the other one might be 4, but those don't add up to be 42. So this one might actually be 3 times 2, and this one might be 4 times 2. So what's that? 6 and 8. But that still doesn't add to 42. This one might be 3 times 3, so 9. And this one would be 4 times 3, which is 12. So that adds up to 21, not 42. So these numbers right here, the 2 and the 3, so the next one would be like 3 times 4, which gives me 12. And this one here would be 4 times 4, which gives me 16. So that's going to be, what, 28? So we're getting closer to 42. And I could keep doing this, but the easier thing to do, we'll say these numbers, the 2, the 3, that 4, this 2, that 3, that 4, those are the unknowns. So these numbers they are reduced, but at one point they were enlarged. They were bigger. But we don't know how much bigger. So because it's unknown, I'm just going to let that unknown be x. So 3x compares to 4x. That still is a ratio of 3 to 4. If the x's are common, so they could cancel out, and we'd be left with 3 to 4. If that's the case, then if this part is 3x and this one's 4x, we could say that 3x plus 4x should give us the total of 42. So 7x equals 42. X is 6. So the number that I would need to multiply this 3 here by would have been 6, and it gives me 18. And this 4 by 6 would have given me 24. 18 plus 24 gives me my 42. So x would have 6x being 6 is the factor that was taken out of 18 and 24 to get down to 3 and 4. Okay, but the two lengths, the initial two lengths, had to be 18 and 24. These questions are, how we just do. There's no context to these stories. They're just proportions, and we're going to use the idea that cross products are equal, or the product of the extremes is equal to the product of the means. So all you're going to do here is you're going to multiply that extreme by that extreme. Now, the only thing you got to be careful with here is that you have a binomial times a monomial, so it's actually 6 times b plus 1. Okay. Then you're going to multiply the means. So put equal sign, and then we go 5 times b minus 1. And now we solve for b. So I distribute, get 6b plus 6 equals 5b minus 5. I'm going to subtract 5b from both sides. So I get 1b plus 6 equals negative 5. B then is equal to negative 11. So if b is negative 11, that is the value right there. That is going to make the left-hand side equal to the right-hand side. So negative 11 plus 1. Negative 11 plus 1 is negative 10. Negative 11 minus 1 is negative 12. A negative divided by a negative is a positive, so it gives me 10 twelfths. Is 10 twelfths the same thing as 5 sixths? I think you guys can reduce this by 2 and recognize that, yes, that is true. But furthermore, if I don't want to reduce, I can just cross multiply again. What's 10 times 6? 60. What's 12 times 5? 60. And because those products are the same, that tells me I do indeed have the correct value for B. These problems are consistent across the board. It's just depending on where your binomials are. If you have binomials, you might come across different algebra and solving. Okay, so in this one, if I cross multiply, that one's easy. It gives me negative 4. When I cross multiply here, it's a little bit more difficult. 3x minus 1 times x plus 2. And now in this situation, what we have to do is FOIL. So we'll FOIL that, which is just the distributive property. So 3x times x gives me 3x squared. 3x times 2 gives me 6x. Negative 1 times x gives me negative 1x. And negative 1 times 2 gives me negative 2. Because I have a 3x squared, because I have an x squared term, I'm going to try to get everything equal to 0. So I'm going to add 4 to both sides. So it's going to give me what that'll add to be 5x. If I add 4 to both sides, that's going to give me a positive 2. Okay. Now in this situation, this is a quadratic, where traditionally when we work with our quadratic equations before, like we just automatically put like x there and x there. But if you think about foiling, that would mean that the first term is x squared. In this case, it's 3x squared. So we run into a little bit of an issue not knowing, do I put x here? Do I put 3x there? Do I put maybe 9 here and 1/3 here? What do we do? Okay. So when that number is not 1, first thing you're going to try is everything divisible by that number. That'd make it easy. In this case, not everything's divisible by 3, so we're not going to go that route. The next route, if you remember, is called the AC method. Okay, so this is your A term, this is your C term. You're going to multiply those together. You get 6. Now you're going to think about two numbers that multiply together give me 6, but add to give us that 5 there in the middle. Those two numbers are 2 and 3. So now what you're going to do is you're going to rewrite this trinomial as 3x squared. That stays the same. The plus 2 at the end stays the same. But now this 5x, you're going to rewrite it as a sum of those two things. So you're going to write it as, and it doesn't matter the order, I'm just going to write 3x plus 2x. And then what you're going to do is you're going to group these two terms, and then you'll group these two terms. And now I'm going to ask the question, what can come out of these two? What do these two have in common? They both have a 3x, so I'll factor a 3x out. And that's going to leave me x plus 1 here. Take that divided by 3x, and it leaves you x. Take that divided by 3x, it leaves you 1. I'm going to do the same thing with the back two. What do they have in common? They both have a 2 that divides them. So I'll take a 2 out. Divide 2x by 2, you get x. Divide 2 by 2, you get 1. If we've done this correctly, if this procedure works, the things in the parentheses should be identical. So now we have x plus 1. The things that are in parentheses, they become a factor. The things on the outside, essentially the coefficients of those quantities, they merge together and they also become a factor. And now we find out, and I'm going to leave this to you, but if you FOILed that thing right there, it's going to come back up and give you that right there. But the reason we have to do that is because I'm looking for two numbers now that multiply together to give me 0, so that means this x plus 1 must be 0, or 3x plus 2 must be 0, so x could be negative 1, or x could be, in this case, it would be negative 2/3. Let's go ahead and see if those values, just to make it a little bit easier, we'll check it in Desmos. If I type in 3x minus 1 over 2, and the right hand side negative 2 divided by x plus 2, okay. Now it doesn't evaluate this because I don't know right now what x is, but we just found x to be negative 1. If I plug negative 1 in, come on, plug negative 1 in, you see that they evaluated to the same thing. Left hand side evaluates to negative 2, right hand side evaluates to negative 2. So negative 1 must have worked. The other x was negative 2/3, so let's see if that works. Plug in negative 2/3 for both x's, we get negative 1.5 for both of them. So we know that both those things are solutions. If your means are, and it's not always the case, but if one set of means is, if they're both binomials, you're going to have a factoring situation. Now, if all four were binomials, you might have a factoring situation, you might not. It just depends on what those binomials are. You might have some cancellation with your x squared terms. Basically, what I'm trying to get at here is that you don't initially know what algebra is going to arise for you. You're going to cross multiply, and then whatever happens, you might get a linear equation, which good, that's what we want. Those are the easier ones to solve. But you might also get quadratic, which then we have to rely a little bit more on our skills from algebra 1. Some key properties about proportions. First one says, if I start with this proportion, it is equivalent to this proportion. And if you kind of look at what we did here, AB is the first ratio in the first proportion. BA is the first in this one. And basically what happens is that AB and BA, those are reciprocals of each other. CD and DC, those are reciprocals of one another. So basically what we're saying here is if we start with a proportion that is true, if we take the reciprocal of that proportion, it is also true. So let's say, for instance, I have, use a different one than what is here so you have multiple examples. Let's go, let's say 5/6 equals 10/12. Okay, first of all, I want to say, is that true? That is true because I cross multiply those, I get 60. Cross multiply those, I get 60. But what this first property is saying is not only is that true, but if you take the reciprocal of 5/6, which turns out to be 6/5, that is identical then to taking the reciprocal of 10/12, which would be 12/10. And the reason that that is okay, because I cross multiply, I still get 60, and I still get 60. So the idea is if I start with A over B equaling C over D, if I cross multiply those, I get AD equals BC. Okay? The property says you should be able to take the reciprocal. So let's take the reciprocal. Let's go B over A equals D over C. If I cross multiply, do we still get AD? AD there. And when I cross multiply these two terms, I get BC. So because the cross products are still the same, that tells me that it is okay to take the reciprocal of the proportion, and it's still a true proportion. That's kind of what we saw that situation in that, I know I've probably erased it, some of that work up here. We did this example. One of the relationships was, I think we created like 3 or 4 of them, was a reciprocal relationship. The next one says that if you look here, what they've got highlighted, all they do is they take those two terms, and those, remember, those are our means, and they replace them, okay, or they interchange them. So what we're saying there, now, it's a little bit different. So let's say that I start with, let's say that 5/6 again. So 5/6 is equal to 10/12. So we know that that's true. What they're saying here now is if you take that number and flip-flop them. So it'd give me, so that would yield 5 over 10 is equal to 6 over 12. Okay, would you guys agree that 5/10, which reduces to 1/2, is the same thing as 6/12, which reduces also to 1/2? Or I cross multiply, I still get, because of the commutative property of multiplication, I still get 60 there and 60 there. So this was the idea. If I have A over B equals C over D, then this would be A over C, okay, equals B over D. If I cross multiply here, I get AD equals BC. If I cross multiply here, I get AD again equals, maybe I call it CB, but isn't, because of the commutative property, isn't CB the same thing as BC? So the argument there is that it is perfectly okay to interchange the means. Now, some people say, well, if I can interchange the means, why can't I interchange the extremes? You can. And here's the argument of why they don't put this in a textbook. If I say that 5/6 is equal to 10/12, the way I write that right now, the 6 and the 10 would be my means. So if I interchange those, I'm good to go. Okay, and that's exactly what we talked about right here. But we know that equations are two-way streets. And we can use a symmetric property actually to rewrite this as 10/12 equals 5/6. Now if I write it that way, now look at what my means are. They're the 12 and the 5, which over here would have been the extremes. Well, if I interchange those, I get 10/5 equals 12/6, and that's a true proportion. I still get 60 and 60. So you can, by all means, interchange the extremes as well, but it's ultimately kind of redundant from to say that in a theorem or in a property. The last one says that you can basically take your denominator, add it to your numerator, and both ratios, and get still a true ratio. So what do we mean by that? So let's start with 5/6 equals 10/6. If I add the denominator to the top, so I get 5 plus 6 over 6 equals 10 plus 6 over 6. the reason you can do this and still get a true proportion. So just combining like terms here or condensing this, we get 11/6 equals 16/6. Okay, so when I multiply these, no, I don't know. This was wrong. This should have been what, 12ths there. Sorry, 12. So this would have been 10 plus 12 over 12, and this then becomes 22/12. Okay, if I multiply these, 11 times 12, does that equal 6 times 22? Times 12, 6 times 22. We do see that they're both 132. Okay, so that's okay. But why is that okay? Well, think about what we really did here. If I'm going to add the denominator to the top and add to the bottom, right now I've got 5 plus 6 over 6. That's a common denominator right there. So this can actually be rewritten. That side can be rewritten as 5/6 plus 6 over 6. Okay, if you started with this, if I gave you a problem like this, most of you are going to rewrite it this way. Okay, we usually like to go from 2 fractions to 1 fraction. This is just going from 1 fraction down to 2, or back to 2. This one here, for the same reason, is 10 over 12 plus 12 over 12. If I had a common denominator of 12, I could add the numerators and get this 10 plus 12. So that goes to that. Think about what we just added here. What's 6 over 6 the same as? Hopefully you answered that question with the answer that 6 over 6 is the same as 1. What is 12 over 12 the same as? 1. Okay, so basically what we're doing here is we're saying we can add 1 to both sides of a proportion and it still be true. Well, think about this. That 1, it really doesn't even have to be 1. It could be any number. It could be 5 here and 5 there, 7 here and 7 there. If I start with A equaling B, if that's an equation, then if I add C to the left-hand side and add C to the right-hand side, that's still a true equation. And that's exactly what we did here. We started with a true equation, 5/6 equals 10/12. And I added 1 to the left-hand side, added 1 to the right-hand side, and I should still end up with a true statement just like that. Okay, so those are some relationships that and properties that my hope is that you spend a little bit of time on and justify to yourself. But you're allowed to find the reciprocal of a proportion, and that reciprocal be true. You're allowed to interchange the means and the extremes, and you're allowed to basically add anything to the left-hand side and the right-hand side. And you can do those in tandem. If I want to find the reciprocal and then interchange the means, I can do both those two things and still have a true proportion at the end. What you're going to find out later on in the chapter is, people are always going to ask me, Mr. Fay, you did it this way. You use these or this proportion. That's different than what I did in my homework, or what you've done on your test or your notes or whatever. And my answer to you will be, okay, well, if you take yours and you either find the reciprocal, interchange the means or extremes, or add 1, 2, 3, whatever it may be to both sides, or maybe do those properties in tandem together, do you eventually arrive at the same thing that I have? Because if you do, then what you did was perfectly fine. Okay? Or we could do that with mine. If can we interchange mine, maybe switch my means, or find reciprocals of mine to where mine eventually looks like yours. And if I do, if we can do that, then that means what I was doing was okay. You're going to see in your homework a couple questions. It says, in the diagram, x over 6 equals y over 7. What ratio completes the equivalent proportion x over y equals blank over blank? So all you got to do is see, okay, well, they took this x and they put it over that y. So we're going to follow the same pattern, and we're going to say that the 6 needs to be put over the 7. Okay, 6 over the 7. One way of doing that is, maybe an alternative way of doing this is say, okay, we said x over 6 equals y over 7. That's what they started with. So when I cross multiply, I get 6y. Cross multiply here, I get 7x. So if I start with x over y equals blank over blank, if I cross multiply, I need to get to that. If I'm going to need to get to that, then the only way that I can get y times something to get 6y is if that something is a 6. So I need a 6 to go there. And the same thing with the x times what will give me this 7x there. Well, the 7 needs to go there. Soccer team played 25 games and won 17. What's the ratio of number of wins to the number of losses? You see this question quite a few times throughout the chapter, or something similar to this. Ratio of wins to losses. Okay, I played 25 games. We won 7. A lot of people are going to say 25 to 17 or 17 to 25, whatever it may be. If I won 17, how many did I lose? Should have lost 8. So then wins to losses should be 17 over 8. Okay. What is the ratio of number of games played to the number of games won? Number of games played would be 25. Number of games won would be 17. That one's a little bit easier than the first one. You guys can do that one. Actually, so that this question is totally void of numbers, but it says in a senior class there are B boys and G girls. Express the number of boys to the total number in the class. Well, boys to total, total is going to be the combination, the sum of those. So we're going to have that. I'll skip a couple of these. Down a couple like that. So a lot of times a good use of proportions is in baking recipes. Even like, I know it's not baking, but it's kind of like like if I'm a concrete mixer, or maybe I'm somebody that works like True Green, or like I got to mix chemicals for like lawn treatments or whatever. I have to be able to work with conversions, because what I used on customer A's lawn, I have to maybe use a different mixture on customer B's lawn, because their lawn might be smaller or bigger than customer A. So the ratio of water to chemicals might have to be a little bit different. Same idea here. Here it says a bucket holds 4 quarts of popcorn. If 1/3 cup of popcorn kernels make 2 quarts of popcorn, how many buckets can be filled with the popcorn made from 4 cups of kernels? Okay. So I'm going to run through this. And it says if 1/3 cup makes 2 quarts. So I'm going to say for every 1/3 cup of kernels, I get 2 quarts. So I'm going to write kernels. I get 2 quarts of popcorn. Okay. It says how many buckets can be filled with popcorn made from 4 cups of kernels? 4 cups of kernels. Oh, spell kernels right. Okay, so what I'm looking for here right now, I don't know this denominator right now, but this denominator, if I think about it, has to be the amount of the quarts of popcorn that can be made out of these 4 cups. So the way we're going to do this is we're going to cross multiply. I get x over 3, I'm going to multiply these, is equal to 2 times 4, so I get 8. So x will be 24. Okay, so that means 4 cups of kernels are going to provide me with 24 quarts of popcorn. Okay. Well, remember the question asks how many buckets. Well, a bucket holds 4 quarts. We right now need an amount of buckets that will hold 24 quarts. So we take 24 divided by 4, and we get 6 buckets. A recipe for making 10 loaves of bread requires 24 cups of flour and 4 tablespoons of baking powder. If the proportions in the recipe are to be used to make 3 loaves of bread, how many cups of flour will be needed? So if you think about this, I believe the 4 tablespoons of baking powder is extra information that's really not necessary. 10 loaves requires 24 cups of flour. Okay, so I only want to make 3 loaves. So maybe in my recipe, we've got a lot of recipes that my family, my grandparents, my grandma used to make this stuff, but she used to cook for a big family. So her recipes were for a large family. If I want to make that food for maybe 2 people or 3 people instead of 10 people or 15 people, I've got to reduce her recipe. So this says that we're making 10 loaves. I only want to make 3 loaves. So how many cups then do I need of flour to do that? So I'm going to cross multiply. I get 10x is equal to 72. So x is going to be 7.2. So I need 7.2 cups. 7.2 cups of flour to make these loaves of bread. I like this question because this kind of gives you an idea of how ratios are actually used in the real world. This is a biology question, like a conservation type question. It says biologists tagged 900 rabbits in Briar Lake National Park. It says at a later date, they found 6 tagged rabbits in a sample of 2,000. Estimate the total number of rabbits in Briar Lake National Park. So they said, so biology, they tagged 900. Okay, so 900 rabbits. Were tagged. Okay, and we don't know of those where those 900 came from, meaning that we don't know the larger population. Okay, so that's what it says. Estimate the total number of rabbits in Briar Lake National Park. So these 900 that we tagged initially come from a larger number of rabbits. Okay, so I'm gonna say I'm gonna write this as 900 tagged rabbits, and this is gonna come from this X that I don't know is the population of rabbits. Okay, which is obviously greater than 900. So that's kind of the first situation. Okay. The second situation is that they let a little time go by and they go back out and they say, okay, we're going to start capturing rabbits again. Okay, and they catch 2,000 rabbits. Okay, so I'm going to put 2,000 rabbits down here, and this is a sample, but the sample is going to help us understand the population. Of those 2,000, they found 6 tagged rabbits. So what we're saying is these 6 out of 2,000 relate back to how these 900 compared to the entire population. Okay, so then if we cross multiply, we get 6x equals to and I'm just going to write this. I'm going to say 900 times 2,000. For the fact that when I do this, if I divide both sides by 6, which is 3 times 2, just to do mental math a little bit here for me, that 3 is going to cancel with there and give me a 3. This 2 is going to cancel there and leave me a 1. So I've got 3 times 1, so 3. I got 1, 2, 3, 4, 5. So we're going to say we got 300, kind of the right spot, 300,000 rabbits in this park based on this process. Okay, I'll give you. It'll probably happen when I come back to school. A technique that we use in biology, and it'll lay out the actual process and what this is called. But that's how we, we know how many, like blue whales are one of an endangered species. Well, it's how do we know how many are in the actual environment? We didn't call like a blue whale meeting and have them all meet up and count them. We go, because obviously that's impossible. We go out, we have biologists, they go out and tag them, and then at a later date they go back and try to capture or tag others, and as we're finding these others in the second later date, we find ones that we've already tagged, and by doing that we can get an estimation of the actual living population. Now we would not want to do this just once. Okay, so 300,000 might be a decent estimate. Okay, but what we'll learn in the statistics class is that we would actually want to do this process many, many, many times, so that we could then take the average of many, 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 many of these situations, and that will give us a better estimate of animals in that population. So let's stop there. It'll be assignment Math Excel over 7.1. Should not be anything that is extremely taxing for you. If you have any questions, let me know.